And so, more than lectures is the way of one's own thinking that one talks about, right? And I hope it's useful to you. I'm not here to instruct or anything. We share certain things, and the way I do it. So, what we're going to talk about is, aim is to talk about DFT, right? Density functional theory. But before we do that, today's lecture is going to be preliminary. I'll set you up for what we are going to do, and then we take over these concepts as to how we deal with them in density functional theory. Right? So the problem we're going to tackle we are looking at is the many-electron. Many-electron problem, and this becomes complicated because of the term. I'm going to use atomic units, makes writing easier. So, and there's my H cross is going to be equal to mass of the electron is going to be equal to E. It's going to be equal to 4 pi epsilon 0. Preliminary. Let's start without this term. So this is going to be 1 over Ri minus Rj. Right? And summed over I and j. So what we're talking about is many electrons they're all interacting with each other. This picture here. All sorts of interaction going on. And that's what makes the problem complicated, but we do step by step. If we first look at non-interaction problem. And the solution that we're looking for in both these problems is the solution of the Schrodinger equation. H psi equals d psi, where the Hamiltonian is going to be summation I minus 1/2 Li squared plus the external Ri plus 1/2 Ij, and this prime is written for indicating, and 1 over Ri minus Rj. And for the non-interactive problem, I'm right now going to drop this term. We'll come to this later. Okay, let's just look at this problem and see how we build up the solution. Alright? So what we're going to do is let me see if I can reduce the size a bit, otherwise I'm getting only 4 lines. So, solve the problem summation I. Is this visible at the back? The size is okay? Yes. Plus the external Ri. That's it. Which I can write as summation sum HI, sum over single particle Hamiltonians, right? Where HI is minus 1 I square plus B external Ri. By B external we mean some potential that is external to electrons. It's not their interaction potential, it could be the nuclear potential, the ionic potential, the background potential, or whatever. Right? And since this is sum over HI, I can write my solution as product wave function. Right? So with this, and this is important, with this, I can use separation of variables technique and write my wave function psi R1, R2 on n as product wave function. Let's use this shorthand. Product over I, phi. Let me write alpha I. Sometimes we write I here and then Ri here, it becomes confusing. Alright? And each satisfies the equation H phi equals sum of sum phi. Very simple, very straightforward. Right? There's no problem in that. So the question is, here's this question right here, are we doing everything all right, even in the non-interactive system? Is this correct? Physically, any comments on that? Very interactive, so yes, no, it's not. Why not? What have I left out? Is that louder? I have not taken?
The interaction with the electron.
No, so that I have ignored, right? I'm solving the non-interactive problem. That part is gone. Coulomb part between electrons is gone.
And phi is just a one electron.
The one electron function. Is this solution complete? So I've ignored two things. One, since we're talking about electrons, spin. Right? And second thing I've ignored is the antisymmetry of the wave function. It may not matter, but for completeness I should write everything correctly, right? So number one, I should write spin. So spin, there are only two variables. I'm also actually introducing notation through this. So in the spin part, I'm going to have some spin, I'll call them alpha and beta, right? And they're measured through some ms. So let me write this as sigma. Sigma is the more usually use notation. This is going to be 1 if sigma is 1/2, that's the z component of the spin, angular momentum, and 0 if sigma is -1/2, so this is the wave function. Beta sigma, let me use a different color for this, is going to be 0 for sigma equals 1/2. 1 equals sigma equals minus. Okay, so this is a function of a discrete variable sigma. That variable takes only two values, plus and minus half, and then I've given you the value. This is one representation. Alright? So, take some getting used to, but once you get used to it, it's fine. And you can already see that the integration, just like integration over x we have in the wave function, is going to be replaced by summation over sigma, right? And you can see that alpha, sigma, since this is real, it doesn't matter. Summed over sigma, alpha, sigma is 1, and so is beta. And there are problems. So that's one part I have to include into the system. Antisymmetry is basically a mathematical way of writing the Pauli exclusion principle. Alright? Now what it says is that no two electrons can have all the quantum numbers the same. So what I should be writing now is actually not this phi alpha I Ri. I should also be writing this as a function of sigma. Right? There is a quantum number sigma and there is an associated alpha or beta. Okay? Just to complete the story, do you know how Pauli exclusion principle was given? What is the motive behind it? Why did Pauli come up with it? Why I'm asking this question is, see, you observe things and how you come up with the principle. Does anyone have any idea why? How? Anybody, any comment? Simplest of things can give you a lot of things. So remember in quantum mechanics, Bohr model came and then Sommerfeld model came. How many quantum numbers did it have? The Sommerfeld model?
What?
The Bohr model had one. It was only n. Sommerfeld had more. It had space quantization. So it had n, it had L, and it had the orientation of the orbit. M, 3. Right? No, Zeeman came later. It was even simpler. And people were wondering how to fill the orbitals so that the periodic table is made. Periodic table was a big discovery, right? I mean, the elements. So then Pauli came up with the principle that there should be one more quantum number and then demand that no electron can have a common quantum number, all the quantum numbers common. And then immediately 2n square comes for n. Okay, the periodic table is clear. And then later, of course, people, connected with Zeeman splitting, people connected with other things. That's how it started. So, I'm going to introduce something called the spin orbits. So with this, I'm also introducing all this, and that's what I'm focusing on right now, non-interacting system, non-interacting electrons, because I don't want to get caught into this interaction part. A lot of this stuff comes from non-interacting system. So the spin orbit, I'm going to call it I, okay, which is going to be a product of phi R. I'm going to call it x, phi of x, times the spin wave function, right? So, what do you call it? Some spin wave function. Sigma. I could depend, so this is alpha and sigma, and this is all alpha sigma. Now, what Pauli exclusion principle or the antisymmetry of the wave function demands is that wave function be antisymmetric with respect to exchange of all quantum, all variables of the electron. And therefore, in non-interacting system, we'll make something called the Slater determinant. But before that, just to make life easy and make it transparent, let's look at two-electron system. All right? If I look at a two-electron system, then particle in a box or helium or whatever, and just symbolically make a potential. There is the ground level. If I solve the Schrodinger equation, upper level, I can have electron up, electron down, that's the ground state, right? In the helium, it will be 1s2. And the wave function, psi, is going to be equal to phi 1s R1, phi 1s R2 times, I can have up and down, so alpha, sigma 1, beta, sigma 2 minus alpha sigma 2, beta sigma 1. This is symmetric with respect to exchange, this is antisymmetry, right? And if you normalize, this is going to be 1 over root. Now notice the moment I write like this, I cannot assign one particular spin to one electron. Electron 1 could be alpha, could be beta, equal probability, right? So indistinguishability of partners also comes in automatically. On the other hand, I could have an electron sitting here, an electron sitting here. It could be up or it could be down, right? In that case, the wave function would be equal to, or let's say this is 1s, 2s. Then the wave function would be phi 1s R1, phi 2s R2. But that is not taking care of the indistinguishability, so I'll make it symmetric. Phi 1s R2, phi 2s R1. But if I make it symmetric, the spin part has to be antisymmetric. Alpha sigma 1, beta sigma 2, minus alpha sigma 2, beta sigma 1. Either that, right, that's an antisymmetric wave function. Or I could have phi 1s R1, phi 2s R2 minus phi 1s R2, phi 2s R1, right? Alpha sigma 1, alpha sigma 2, right? Or the same thing, beta sigma 1, beta sigma 2, or the same thing, alpha sigma 1, beta sigma 2 plus alpha sigma 2, beta sigma 1. Right? In all this, what you will see, if you calculate the expectation value of s square in this case, s will come out to be 0. So 2s plus 1 is 1, this is a singlet state. Okay? And here, in this case, ms will come out to be 1, s will come out to be 1, ms in this case will come out to be minus 1, s will come out to be 1. In this case, ms will come out to be 0, s will come out to be 1. So this is 3 states of the same thing, 2s plus 1 is 3. Alright, any questions so far? And this is all non-interacting. There is no interaction so far. Okay, I've taken the Hamiltonian where particles are not interacting. All I'm doing is taking care of the spin, and I'm also taking care of the symmetry of the wave function. Any questions? Any comments? Okay. So once you have the similar triplet, right? Still, what I'm doing is I'm writing these as product wave functions because particles are not interacting, and all this. All these three are derivative. They have the same energy. The energy comes from phi. That part is the same, right? And here, in fact, no difference is going to come in between the energy in this and that because there is no interaction. Interaction actually splits. All right? Okay. Now you see that I'm trying to make an antisymmetric two-electron problem, and this is what I'm getting. What about an electron? How do I do it systematically? Okay? So let's do that. This is where the spin orbits are going to come in. So what I'm going to do is let's focus on a singlet. Or one of those, and write the wave function psi as a determinant of, remember the spin orbital that I introduced. Just to remind you, the spin orbital is product of phi and this spin part of the wave function. Right? Because when I do the antisymmetry, it has to be the exchange of all the coordinates of the two electrons. So I have to take care of the spin as well as the space part. So this is going to be chi, let's say 1, x1. Chi 1, x2, all the way up to chi 1, xn. Alright? Then I write chi 2, x1, chi 2, x2, all the way up to chi 2, xn. And keep doing it until I hit chi n, x1, chi n, x2, all the way up to chi n, xn, and take it together. And there will be some normalization concept. By the way, all that I'm doing, I'm going to be leaving some steps, or maybe I'll forget some steps, but they will be covered in your assignment. And I've already given assignment and emailed the copies to everybody. Yes, there are 10 copies, and then others we don't know. Alright? Now, okay, so this is known as Slater. Determinant. And you can see if I change x1 and x2, right, to change the sign. Right? So it's antisymmetry. With respect to exchange of xi. Right? And that's the requirement of antisymmetry. If any two spin orbits are the same, it becomes 0. So no two spin orbits are the same for any electron. Each electron has its own spin orbit. Is that okay? So this, if you really like, is a linear combination of all the possible permutations of I1, x1, I2, x2, all the way to chi n, xn, and then I commute these x1, x2, and so on, and multiply by -1 raised to p, where even permutation is positive, odd permutation is negative, and sum over. That's another way of writing it. Right? And this is also, this, you can call it antisymmetry operator. So the antisymmetric operator of acting on I1, x1, I2, x2, all the way to pi. Usually we learn about Slater determinant when we are taught Hartree-Fock theory or interacting problem. But Slater determinant is always going to be there, interaction or no interaction. Okay, any questions so far? It's just that it doesn't affect the energy, but this is the correct way of writing the n-electron, non-interacting electron wave function. This is the correct wave function. There is still a problem with it, and you will see. I think I have given one of those assignment problems. Yes, this will be problem number 3. There are written about writing symmetrized singlet and quadruplet state wave functions, which I have written. Can all those be written as single Slater determinant or a linear combination? So that is for you to think. Nonetheless, this is the minimum you should be doing for even a non-interacting n-electron system. Is that point clear? Right? Because even for non-interaction, this has repercussions. Any questions? Okay. So now let's see. How do we calculate expectation values? Okay, and these are basically known as Slater groups. Okay, this is in general, but I'm just going to talk about a single Slater determinant. We are not replacing anything. So, if I have this psi SD, all right, some operator ISD, alright, this is going to be equal to diagonal term I1, x1, I2, x2, all the way, the operator, and psi SD. Okay, so this is going to be, if I write it openly, integration dx1 dx2 all the way to dx n I1 star x1 I2 star x2 all the way up to n star xn times a summation over p minus 1 over 1 raised to p, right? Commutation of all this. There are going to be n factorial terms. Okay, so I first thought I'll give you a proof for this. Let's see. I'll leave it for you, just giving you some steps. What we are calculating in this is essentially summation minus 1 raised to p prime. I'll write the first Slater determinant. Summation to p prime. All this I1, x1, diagonal term, right? Then I have minus 1 over raised to p. P diagonal term. And sum of p prime. Is that okay? And then I'll just write, I can always do that. I'll write p prime equals p times some p double prime. Okay, I can always write a permutation as combination of two permutations. Right? And therefore, minus 1 raised to p prime, minus 1 raised to p double prime, minus 1 raised to p. And you get summation over p, summation over p double prime, minus 1 raised to p double prime, p double prime, this thing, and then there's going to be minus 1 raised to p, minus 1 raised to p, so that's 1, right? Another combination. Okay, so you are taking, I can just write it like this. I can even write it outside. You're taking a Slater determinant. Each term you're computing, and you're computing this thing by exactly the same thing. So all terms are going to be equal. So I can write this as, so there are going to be n factorial permutations. Right? Because all things are equal, right? This diagonal term times the Slater. No holes. Or the holes somewhere. Or the holes. Operator. Right. And O is symmetric with respect to the permutation. Okay? So then you can think about it. I'll just give you the default outline as to how to work. Alright? Any questions so far? Okay. Now, if there are no questions, you can just work out a few things. Yes. Louder. All right. I've been a little careless. It doesn't really matter. This is operating on the things inside. It's operating on each one. Doesn't matter. Once you have that, I can calculate. So let's calculate C normalization. Remember I wrote this rate function psi as C normalization times the determinant. For C normalization, O is 1. Right? If O is 1, I'm going to get this term, diagonal term will go with only the diagonal term. This gives you 1. So this SD, psi SD is going to be n factorial. So Cn is going to be 1 over square root of n factorial. So your wave function psi is normalized wave function is n factorial square root times.
This is only assuming that each single particle state is distinct.
Each single particle state is
Distinct.
what? Distinct.
Yeah.
Well, they are distinct because you cannot otherwise tell Pauli exclusion. Otherwise, the wave function will be 0. Right? Okay. Then I can calculate the density rho r. In that case, density operator applied in the different color. Let's be colorful. I was thinking if green will work, that's right, it should not work. That will work. And you change the color. So, density R, the density operator, summation I, delta R minus Ri. Is that okay? Right? And in fact now, if I do this actually is a little problem here. Okay. Yeah, that's okay. So I'll have rho r is equal to n factorial and 1 over n factorial, right? And then you have y1 x1 all the way to pi n xn delta r minus Ri, the Slater term. So anyways, normalize this will go away. And there's some over I. Okay? Just a little thought will contribute when all the sums are just in the right order. This actually will come out to be summation over sigma yi r. In fact, now that we're talking about Slater modern rules, I just calculated this. So let me write a general rule. That is, if I have O as a single particle operator, that is summation, sum f I. Okay, that's what this is. This is a single particle operator. Okay? Then psi, O psi, and I'm assuming that psi are normalized, will come out to be phi I, f, phi I, some rule I and sigma. I think this is right, I that includes both sigma and f all the quantities. Alright, that's what I used here. This is general rule. So your f would be, for example, kinetic energy operator will be summation I minus 1/2 del I square, right? And notice this I is gone because here is R, it becomes a dummy value. Okay, this you can just go home and work out. I'll be available since morning till evening in my office. If you don't figure it out, I'll be there. Then if I have a, so let me write this O1, O2, and we'll stop at O2 because two particle operators is the maximum that I need. I'm going to write this as summation G I j I and j I not e. Alright? And now I'm going to calculate something very important using this. Remember, I'm still calculating things for non-interactive system. There is no interaction. So where does Vij come from? What will be the two particle operator out here? Blue one. I'm going to calculate. Blue will not be visible at the back. Any answer for that? Why is blue not visible at the back? Raleigh's law of scattering. So, I'm going to calculate P2, which is the probability of finding the particle at some point r prime if I locate one particle at r. So, I'm locating one particle at r, trying to find another particle at r prime. Now j could run from j equals 1 to n minus 1, because I've already located 1 at here, and then I average over I, so this is going to be I equals 1 to n. And I'm going to call this P2 R prime. Probability of finding one particle out of all these n particles, right? So this is an average over these n, so there has to be something more. So I'm talking about probability. So this is average over n. This is average over n minus 1. So I have located a particle at r, and from the rest, I'm trying to find a particle at r prime, and probability is this. If you feel more comfortable, I'll write in expanded form, and the expanded form is I take one particle at r, right? Then I find one particle from the rest at r prime divided by n minus 1. That's the probability of finding one of the particles from those n minus 1 at r prime. And then I average over I, because I don't know which particle I'm locating. That's a two-body problem. Alright, and I is not equal to j. J is not equal to I. Right? Because once I have fixed the ith particle somewhere, I cannot locate it from the rest of the particles. And that's the two probability I'm going to calculate. Is that okay? Any questions on this? Remember, I'm still doing non-interacting problems, no interactions, but still there's a lot of structure in it. So, let's do that. So I'm calculating this diagonal term, chi1, x1, chi2, x2, and so on, chi_n, xn. Gij, let me write explicitly, means Ri and Rj, and the Slater determinant. In the Slater determinant, all the terms have to be in the same order. So I'll have one direct term. However, since there are these two, I can even have a non-zero value if I split all this. I1, x1, g, ri, rj, I1, x1, all the way up to, I can have chi I at j, chi j, xi, chi n, xn. Still I'll have non-zero because Ri and chi in with j will not give me zero because this is like I'm calculating some function, right? Ri rj integration phi I ri phi j rj phi I rj phi j ri. If this term was not there, this is orthogonal, this would have been zero. But because of this term, it's not zero. The only thing is out here, because these are spin orbitals, if the spins of I and J are different, it will be zero. The formality of those wave functions. So in the second term, I have to have sigma r equals sigma j. Because of the orthogonality of the wave function, of these spin wave functions. This is a little subtle, so I'll wait here and see if there are any questions.
So you actually have only two terms.
I have only two terms.
And the second one is with I and j.
Exchange. One direct and one exchange. And with the spin being the same. Okay, now let's put the value of G, I, R, J in there. And what I get is 1 over n minus 1, right? And I'll get summation sigma phi I sigma r square summation sigma I phi j and j also r prime more square minus summation sigma, okay, this could be sigma prime, it doesn't matter, but here the sigma has to be the same. I'll have phi I r star phi j r prime star, sigma is all the time the same, phi I sigma r prime phi j sigma r. Summation I, summation j. Notice the difference. Here I'm summing over sigma and sigma prime both. Here the sigma is the same, so I end up with only one sigma. Okay? One more thing. Nobody asked me. Here, I was not equal to j. Then I'm not putting any of that condition. That's because I equal to j term cancels. I have added some that the same. It automatically cancels. Is that okay? Alright. Once you do that, let's write this more systematically. I have P2 over n minus 1. Inside I have rho r, right? This is summed over all the occupied orbitals with all the spin taken care of. Rho r prime minus summation sigma, I and j is only for the space part. Phi I sigma r star, phi j star r prime, phi I sigma r prime, phi j sigma r. Alright? I'm going to write this as rho r over n, 1 over n minus 1, integration, rho r prime minus summation sigma, summation ij, all that, right, divided by rho r, all that, let's write this, phi I r star sigma, phi j sigma star r prime, phi I sigma r, phi j sigma r prime. Okay? So, this. Product of two terms. The probability of finding a particle at R is density divided by n. That's very simple, right? Once you have found a particle at R, probability of finding another particle at R prime is this complicated anyway. Right? So just because you have this antisymmetric wave function, there are these subtleties which come in. Right? Now let's understand this. Suppose all these particles would go through anywhere. There's no antisymmetry, nothing, they were just moving freely. Then P2 R prime would have been probability of finding a particle at R would have been this times the probability of finding another particle at R prime, and they are going all around. There's no connection. So this would have been the density for n minus 1 particles would have been divided by n times n minus 1 divided by n minus 1. This will be nothing is happening, right? Which would have been just rho r divided by n, rho r prime divided by n. Right? Now, however, this thing in the brackets, in this null has been replaced by this. The density of finding a particle at R prime is not just proportional to rho r prime. It is rho r prime minus some subtle thing, right? And this, what does this integrate to? If I integrate this over r prime, this will give me n, it integrates to n minus 1. This will give n minus particle. Integrate this with respect to r prime, and you will find this is also n minus 1. Right? This is n minus, if I integrate over r prime, it will give me delta ij, and that will give me the density that I can see. I'm going to write this as rho r over over n times 1 over n minus 1 rho r prime minus this complicated animal, which I'm going to call the exchange mode. That means, in this picture, if I had this density of electrons and I fix one electron somewhere, then the other density would be just slightly less, but uniform. Is that okay? That's what it's showing. The same density, just scaled by n minus 1. Right? On the other hand, if I look at this you can calculate for different wave functions. It is, initially suppose the density is like this, and if I put an electron here, it makes me a structure. And this e raised to 1. But I'm subtracting, so it should be positive. This is minus. Okay? So here, everywhere, it didn't matter, everywhere it went down by a factor of n minus 1 by n. Here is my sorry. And this is the known as this. Each electron is moving around with this deficit of one electron, which is structure, known as formidable. And how much does it go down by? Formidable. You can check immediately. Rho x r prime is exactly rho r by 2. R prime equals r. And integration rho x r prime is equal to r prime is equal to 1. So deficit is of that one electron, which it should be, because I've taken one electron away. I fixed that somewhere, right? And the deficit right at the electron position is rho bar by 2. Why is it not rho? Why is it rho bar by 2? Any observations on that? You see, this is arising from the same spin. Same spin. Other spin doesn't get affected. So it's the same spin electrons that keep away, that create that rho. The same spin density is rho r by 2. Okay? So this is non-interacting but very subtle. Even in a non-interacting system, what I have is, here is all these are going around, but if you look at carefully, if I calculate the probability of finding an electron somewhere, given an electron somewhere, then there's a structure, there's a hole. Any questions so far?
So Pauli's name is not there. There's nothing like Pauli would. Never hear that.
There's Pauli potential.
Yes, there's a Pauli.
Okay? So even in this non-interacting system, because of the antisymmetry or the Pauli principle or the formidable statistics, there is a specific structure. Right? Imagine this.
So when you just look at two electrons.
I hold one electron, I mean kind of, yeah.
And so suppose you fix an electron and you're looking at where you can place the other electron. So some region is coming into you.
Some regions, parallel electrons are not coming.
Around the electron which you have fixed is kind of a bit into you. But when, so this is fine, this picture is fine, but when you look at n electrons together,
yes.
So then, like, if I do the exercise of placing the electrons inside a plane or a box, so I have fixed So initially every point is available to me for the first electron, suppose.
Yeah, somewhere electron is somewhere.
The second electron can't be at
Second electron the same spin.
Can't be. Similarly, do this, keep doing this until you get to n electrons.
That's what I did.
So this will how does the continuation of this look like for n electrons? Like
This is an
the position of nth electron will be affected. Like does it see
These are indistinguishable particles. So all I can say is, if there's a probability of finding a particle somewhere, then the probability of finding other particles around it is different. And I've averaged over all particles. This is an expectation value. So this is an average. I'm not talking about first electron, second electron, third electron. I'm not talking about summed over I, summed over j, 1 over n.
Does each electron see a hole at around every?
Yes, because each electron has n by 2, n minus 1 or n by 2 minus 1 electrons to around it, which are excluded. But it has a structure. All right? Anything else? So I wanted to do this.
So is that the reason why we can say that actually it's not a particle, it's a quasi-particle?
Yeah, they are moving around, there's a wave, so you can say that. Right, so usually this is done when you do interacting electron problem, but I do want to emphasize that all this structure is without it. The way it affects interacting problem is, imagine this. Suppose we still have the same wave function, approximate wave function, right? Suppose I still have the approximate wave function. If two electrons are interacting, right? Usually you write interaction electron energy as rho r prime divided by 1 over r minus r prime. But now this guy sees very less electrons here. The energy goes down. That's the exchange energy. Okay, we'll work it out. But all I have to do for that exchange energy, here I had calculated for delta r minus r prime. I'll just have to put 1 minus r I minus r j. Okay? So this is what is without interaction. This is non-interacting electrons. Okay? Now we are going to introduce interaction. Okay, so just keep in mind, even non-interacting electrons are moving around with this deficit. Now it may so happen, let me just go a step, jump the gun a bit. If electrons are also interacting, in addition to this spin or relation, there will be, it will repel other electrons also, then the whole may go together. Okay, and that is known as exchange correlation hole, but that can be derived exactly, except that now you have this physical picture. The electron is going around to this hole, and this hole will become even deeper. Okay, except that the charge neutrality or the condition of one electron being excluded still has to be satisfied. So this is linked to 1. Alright? Okay. So this is as far as I come on the non-interacting part. Now let's come to interacting problem. First question we ask